Hi, and welcome to a deeper dive into Explain. I am Michael. I'm half the team behind a tool called PG Mustard, which helps people review Postgres's explain analyze output as quickly as possible. As such, I have spent a lot of time in the last couple of years looking into explain plans and behind the scenes into explain. Um, my background is in product management and quite a lot in database tools at a company called Redgate. In the bottom left there, you'll see a glossary of terms for explain I put together last year. I spent quite a lot of time on, so that's a good reference guide. And there's my email address and my handle on a lot of the Postgres communities, Twitter, that kind of thing. So yeah, do feel free to say hi. It'd be great to meet you. Wonderful. So today we are going to be picking up from where a lot of the other explain type talks leave off. So we're not going to be covering the basics. If that's what you're after, I do highly recommend a few things listed there below. Naturally, the Postgres documentation itself is really good. That gives a really good but quite brief introduction, and there's a chapter called Performance Tips. There's also a really good blog post by Thoughtbot on reading explain analyze output. And there's a 50-minute talk by Josh Burkus that I really thought was great. And in that, he covers a lot of the real basics. And even in 50 minutes, he couldn't get to some of the stuff that I'm hoping to cover today. So yeah, highly recommend those. But so what are we going to cover is a couple of things. One is some of the less intuitive calculations you're going to have to do in order to work out, for example, where the time's going or where the bulk of the work is going. What explains why the query you're looking into is perhaps slower than you want it to be. And then in addition to that, so once you've got the calculations sorted, what kinds of issues could you be looking out for, and perhaps not just the few that you might be most familiar with. So I'm going to try and skip over those and move to some of the less common ones. Wonderful, yeah. So in short, help you determine why is this query slow and what could you do about it. Great, so to start off, we're going to look at loops. Now, hopefully this is something you'll at least come across. I think most places mention it in passing, that a lot of the statistics you'll be looking into are per loop average. So for example, if you're doing a nested loop, the second part of that will be looped over multiple times, and the statistics need to be multiplied by that number in order to get the total for that operation. So yeah, that includes some pretty important numbers like the costs, the rows, and the timings, but not, for example, the buffers. So we'll cover that a little bit more later, but it's important to know that some but not all of these numbers are per loop averages, and they are means. So basically most of the time rounding doesn't matter. So costs and timings are to quite a few decimal places, and chances are you're not going to be too worried about roundings to those. But rows are an integer number. So if you've got a high number of loops and a low number of rows, you can get quite a lot can be hidden by the fact that it's a mean. Wonderful. So yeah, firstly, a quick disclaimer. We're going to be looking at quite a few edited query plans, mostly to fit them on the slides, but also to hopefully draw your attention to exactly the parts we want to look at. So yeah, please forgive me any creative licenses taken, and there's a chance I've made a mistake or two as well. So yeah, apologies in advance if that's the case. Fantastic. So first example we are going to be looking at is this nested loop. You can see here that we're focusing on the row numbers and taking those loops into account. So in this case, we're doing an index only scan. Oh yeah, you'll also notice that if these have ever come from real world examples, I've completely anonymized them. So yeah, so index only scan returning 9 rows, and then for each of those we're looking up in an index using this index scan. So we're looping over that 9 times. Now, to get the number of rows of that index scans returning, you could, in theory, multiply 9 by 10 to get to 90 rows. We can, in fact, see that from the nested loop operation above that the more accurate answer is 86 rows. Now, this is not a big discrepancy, but you can already see where rounding issues start to creep in. So yeah, not too bad in this case, unlikely to point you in the wrong direction or cause you any issues while working out where the main parts of the slow query are here. But yeah, hopefully a good starting point. Wonderful. So next up are threads. Very similar to loops in that the costs, rows, and timings are all per thread as well. And they are shown as loops, in fact. So the same calculations before apply here. An important additional piece of information that does trip people up from time to time is that the number of workers you see is not the same as the number of threads because the leader is not included in that, or the main thread is not included in that. And I'll show you an example in a moment of how you can work out that main thread statistics. So yeah, a tip here is to use verbose. That can give you some extra information, thread-related information, as well as a few other useful things at the cost of making the output more verbose. But yeah, useful for in-depth performance analysis. Great, so an example, we've got here a parallel sequential scan across 3 threads. We get that from the loops number there, but you can also tell it from the fact we've got 2 workers, worker 0, worker 1, plus your main thread. So you'd be forgiven, I think, on this sequential scan for looking at it quickly and assuming it's returning, what was that, 63,500 rows? But in fact, you need to multiply that by 3 to get the total output here. The leader, or the main thread in this case, you can calculate its statistics by subtracting the workers. In this case, we're looking at the simple case of rows, and you can see that the leader's doing a bit more work than each of the workers, returning 76,000 rows in this case. Wonderful. I mentioned briefly that buffers are not a per loop number, and like the others, and I did skip over this because it's normally covered in other introductions, but all of these statistics are inclusive of their children operations. So, very simple example here. This is the same nested loop as before, except this time we've requested buffers. So we've done explain, analyze buffers, and you can see here that firstly, the index scan is hitting 101 blocks. That is not multiplied by 9. So it's not 909 in total, it's 101 across all 9. And then in addition to, so if you add that to the index only scans buffer hits, you get to 105, and therefore you can tell that the nested loop, as expected, is not doing any additional reads. Great, so I left the fun one till last. This is the last one on the arithmetic front. But yeah, timings, so this is specifically per operation timings. So you do get at each level the the time inclusive of children that you sometimes need to multiply by loops. But we're also going to look at when simple subtraction doesn't always work. So yeah, it can get tricky, and we'll look at a CTE example. But yeah, it's worth noting that even for tools that you use, this can be tricky, and it's worth being aware of where the traps lie. So perhaps when you should be double checking. Great. So first, a simple example. Back to our nested loop. This time, if you look at the numbers in bold, and remember that you're subtracting the lower down nodes from the top one to work out the nested loops contribution, you'd be forgiven a quick glance for thinking the majority of the time's coming from the nested loop operation itself. But once we remember we've got 9 loops for that index scan, that now takes the majority of the time. So with 0.27 milliseconds, I know the numbers are tiny in this case, but 0.27 milliseconds subtracted from 0.368, and then also subtracting the small contribution from that initial index only scan, we get to 0.079 milliseconds. So a lot less than the 0.27 milliseconds of the index scan. So yeah, that was a simple example. And for a slightly more complicated example, but the simplest version of it I've come across, and credit to Felix Geisendörfer, who was very gracious in helping us work through some of these things when we were first fixing them in PG Mustard. This is the simplest example I've seen of a CTE that is referenced twice in the query, which involves an optimization. So Postgres can do the CTE only once and then refer to it back to it multiple times. Neat optimization, but it causes some complexity when you're trying to calculate timings from the query plan. So let's look at that. Now, with this simple example, as a human reading it, you can quite quickly work out what's going on, and you can see that there is some double counting. You can see that that first function scan's about 100 milliseconds, and you can see the second one's about 200. You can see the limit's about 100. You can see the CTE scan B is about 200. So it's not hard to work out that these don't sum together to be 600 milliseconds. They are in fact double counted, and the total time is 300. But yeah, it gets complicated quite quickly around CTEs, recursive CTEs, init plans. So if you've got any of that and you're wondering what's going on, or if your tool's telling you some weird stuff, worth remembering that this could be the kind of thing that's going on. But there are other cases where I've seen things make mistakes, especially around gather operations and things with lots of children. So if you're seeing some weird timing stuff, worth checking in a second visualization tool. And yeah, if you want to know more about the CTE case in particular, I think that could be a talk in itself, or at least all of these kind of edge cases. Felix has done a really good write-up on his Flame Explain website under quirk correction. Yeah, so as I mentioned, there are lots of tools out there, way more than I could fit on a slide, for helping with this kind of thing. The popular ones I see a lot in some of the communities are Depez's tool, which is, I think, by far the oldest on the list. He's been going for lots and lots of years. It's super helpful for giving people a quick visualization of the text format, as well as trying to calculate some of these per operation times and a couple of other simple things. Dalibo recently took the baton on from Alex Tatiants on the PEV front, so Postgres Explain Visualizer. So they've built a great visualization tool. The one I mentioned earlier from Felix, Flame Explain, shout out to our fellow calculations nerd there, and PG Mustard is the one that I work on. So yeah, I would highly recommend trying a couple of these if you've got any weird things, especially around timings, trying to work out where the timing's going. If you're anything like me, we created this because we didn't like doing these calculations in our heads. So yeah, hopefully these can help. But yeah, next up, so after arithmetic, so you've worked out roughly where the timing's going, you've worked out where the bulk of the work is maybe, but you then need to figure out why, like what can you do about it? A lot of the other materials I've mentioned do cover some of the biggest issues you'll come across, or the most common perhaps. That includes a missing index, so perhaps a sequential scan on a large table that's filtering out a lot of the rows before returning. Bad row estimates can be a huge issue in terms of how Postgres thinks, how many rows Postgres thinks are going to come back, and therefore which strategy makes most sense for it, which would be the most efficient. And sorts and hashes spilling to disk, much slower than if they can be done in memory. So I think these are pretty well covered elsewhere. So I'm going to skip, not give examples for those ones. Onto another case where large filters. So this is, I guess the key takeaway here is just because you've got an index scan doesn't necessarily mean it's efficient. And the way to spot this is looking out for rows removed by filter type things in your explain plans. Big thing to look out for is the number of loops. So these filter numbers are per loop average again. with all of the caveats we mentioned around where you can get tripped up around means. So watch out for especially low numbers of filters and high numbers of loops. Got a much more simple case here though, where we only have one loop. So this index scan is returning 1,000 rows, but to do so, it's having to remove 3 million. Now, if you want a number to associate that with, you could say this index is 0.03% efficient for the query. And if you can work out a way to get those 1,000 rows in a more efficient, well, without having to filter out that many, chances are it'll be a lot faster. So yeah, look out for large filters. So in this case, we've got rows removed by filter 3 million, or even if that number's low, but the loops number's high, look out for that as well. Fab. So next one to keep an eye out for is the lossy bitmap scan. So I imagine you're probably familiar with bitmap scans. They're a really cool feature in Postgres. In order to do their job, they do need to keep a bitmap of the, in the best case, the tuple IDs of which rows contain the information they're looking for. But if that a bitmap would get larger than your setting for work mem, which is quite low by default in Postgres, 4 megabytes. So if it would exceed that, Postgres reverts to a lossy bitmap scan, which means that some of the pointers are to a block instead of to the row. That means it gathers more rows than it needs to, assuming some rows in that block wouldn't satisfy the filter condition, but it still fits in work mem. So it's a trade-off, but if you can avoid it, your chances are your query will be faster. And yeah, so these are a total rather than a per loop average. Great. So an example here, you can see the things I've highlighted in bold are the rows removed by the index recheck, which is 5.9 million in this case, and the lossy heap blocks. So the exact heap blocks are the ones that are able to be done in memory, and the lossy, or the exact point, so the pointers to the exact rows, and the lossy ones are the ones that had to be done to a block instead. So the proportion of those is quite interesting. If you've got any lossy blocks, you could maybe improve performance, but if you notice that it's the majority or a large majority, then there's a big chance that this is an area you want to look into. You can see above, I haven't put it in bold, but the rows returned by this operation are about 3.9 million, 3.85 million up there. So we've read in an extra 6 million when we wanted to return 4. So about 60% of the work we're doing here is waste, or it's inefficient, let's say. And naturally, these are big numbers, and if you can work out a way to filter down to the rows you really want quicker, that's always going to be better, or generally going to be faster. But in this case, there's a big opportunity. Wonderful. So another issue to keep on the lookout for that does require you to use that buffers flag that we mentioned earlier. So at minimum, explain, analyze buffers, is a lot of data being read for the amount returned. So this isn't an exact science. There's a couple of these numbers are estimates, and even in the best cases, you can, like, let's say we wanted to return a single several byte field, we'd still need to look up a minimum of 8 kilobytes, given that's the block size. But at scale, you can start to spot really big problems with using this approach. And it can, as I've mentioned here, be a sign that the table or index that you're scanning is bloated. Wonderful. So here's an example of how to calculate that. You can see that we have an index scan here, and I've highlighted the width, the rows, the loops, and the buffers. So firstly, to see how much is being read, we can look at the buffer numbers. Here we've done a simple sum of those, and multiplied it by the block size, which was 8 kilobytes, and that's a total of 10 gigabytes of data read in this case. The amount returned we can estimate based on the average number of rows, which remember could be anything, well, it's 1 in this case, but it could be anything from 0.5 to 1.5, so it's quite a big variance even in that number. Multiply that by the number of loops, multiply that by the estimated average width, which in this case is, well, it's in bytes, but in this case is 8 bytes, and we get a total of 2 megabytes. So huge discrepancy there. We've read 10 gigabytes of data to return 2 megabytes, something to look into. Wonderful. Right, now, the last few that I'm going to take you through are all related to the summary section at the bottom of the query plan. So, most guides do give you the advice of starting at the bottom of the query plan, working your way up, but I would add to that make sure you pay close attention to that summary section, because especially if you've got a complex query plan with lots of operations, the types of issues that can show up in the summary are so big, they're very often the dominant issue. So when I say very often, when they exist, they're often the dominant issue and can avoid looking into the rest of the plan entirely. So first up is planning time. Now, as the name suggests, this can be planning related and often is. So it could be the number of joins that you're doing in Postgres, having to look through all the permutations of which order would be best to do those in. It could be partition pruning related. And I admit I don't fully understand this. I believe, and I've seen people mention that this can also be extensions reporting some of their overhead as planning time, or even Postgres waiting on locks and reporting that as planning time. Last thing from me on planning time is a quick warning that the extension auto explain, which lets you log the query plans of your slowest queries automatically behind the scenes or into the logs, doesn't report planning time. So you can't spot this category of issue through auto explain. Wonderful. So nice simple calculation in this case, but you would I think you'd be forgiven for thinking that planning time was included in the total or execution time. But as you can see from this example, or any example where planning time dominates, it doesn't. So yeah, you can see here it's accounting for 71% of the total time, at which point there's very little to be gained from optimizing anything above that in the query plan. So yeah, gives you a very quick guide as to what the problem could be. If you suspect if it looks fishy and you don't think it's complexity related, maybe run the query a few times just to rule out some of those other potential issues. But yeah, this is how to spot it. Next one that's included in that bottom summary section is just-in-time compilation, or JIT. So this is included in the execution time and in the times of the operations. You'll see it in there. I'll show you an example in a moment. Worth noting that this was introduced in version 10 of Postgres, but it was turned on by default from 12 onwards. So if you're doing an upgrade from before 12 to after 12, I would highly recommend just keeping an eye or checking what the whether you're gaining or losing as a result of just-in-time compilation being turned on by default. So how would you spot it? You can see it's sandwiched in here between the planning time and the execution time. So again, right at the bottom of the query plan. The total is what I'd recommend just taking a quick look at and seeing what proportion is that of the execution time. 52% is obviously quite a lot. I've seen bigger, so it can be the dominant issue, and I've also seen people in the communities, quite a few reporting that for them turning JIT off was ultimately the better approach. But yeah, it's on by default for a reason, so there's a good chance it's doing you favors, but something to be aware of. And yeah, another kind of, if you've if for any reason you've not seen it at the bottom there, or you're looking into something somebody else has sent you, and you spot something like this, which is a very suspicious startup time for a sequential scan in this case. So this was a leaf node in the example I just showed, so from the same example. And this is a very small sequential scan of 54 rows, only 3 buffer hits. So it's doing a very tiny amount of work, and we'd expect perhaps even a 0 startup time, or very, very low startup time to return that first row. But instead we're being told it's 2.26 seconds. Super suspicious. Turns out in this case it was JIT related. So that's another way you can spot these things. Wonderful. And the last one on the summary section, or I think the last one we're going to have time to go through today, is triggers. So these are also reported at the end of the query plan when they're present. You might, even if you don't use triggers, there's a chance you'll see these due to how constraints are implemented behind the scenes. It's worth noting that the timings you'll see are across all calls of the trigger. I think that'll generally be quite obvious when they're the dominant issue, but just in case you're looking at fast ones and you're not sure. Before triggers and after triggers also have a subtle difference in how they're incorporated into the rest of the query plan. So after triggers are included in execution time, but you won't spot them taking up any of the time in the rest of the query plan, whereas before triggers are included in that first, or the top node. So like the root node will include any time from before triggers. Brilliant. So super simple example again. All we're looking at here is the total time of this constraint trigger. Actually, something I didn't mention that was on that last slide was if you do spot these constraint triggers and they're related to a foreign key, a lot of the times these are slow is due to, or a lot of the times these could be sped up by adding an index on the foreign key. So worth remembering that's not done by default in Postgres. Great. So what's the proportion of trigger time in the total time? In this case, 95%. We've already found our problem, or at least our bottleneck, and we don't need to read the rest of the quick plan. Wonderful. So in summary, my advice would be to first check the arithmetic and be a little bit suspicious once you've got lots of loops going on, CTEs, init plans, that kind of thing. There are a lot of tools out there that can help avoid you having to do a lot of this mental arithmetic, but it's hard. I could tell you, I promise you it's hard, and therefore, if in doubt, I would highly recommend checking a second one. The second part was, don't just look for sequential scans, or remember that there are a lot of other things you can spot through Explain as well. So don't give up once you've run through the few issues you've seen before. Do look into what you found to be the slowest operations. See if there's any extra information you can get that would help you diagnose it. Yeah, so specifically, check the end section. Make sure you do check that summary section. Look out for filters on other operations, not just sequential scans. Index rechecks, lossy blocks on those bitmap scans, and the total amount of data read. So highly recommend. In fact, yeah, I didn't mention this, but buffers is not on by default with Analyze, but there are a lot of people, including myself, who think it would be really helpful if it was. So it doesn't add a ton of, especially once you're already doing Explain Analyze, it doesn't add much overhead. So I do highly recommend whenever you're doing Explain Analyze to do Explain Analyze buffers at minimum. And yeah, if you get stuck, there are a lot of resources available, including the Postgres performance mailing list and a bunch of communities. So Slack, IRC, Reddit, even Discord now. So yeah, a lot of helpful folk there. Once you've ruled out, once you've got as far as you can get. In terms of further reading, I did want to give another quick shout out to Felix's quirk correction post. That's the link below that is our glossary on all of the terms you might come across. So each operation, each of the different fields. So if you do find that you think a field might be suspicious, do search it or look it up in our glossary, and hopefully there'll be the information you need there. So things like what unit is that in, whether it's a per loop average, what links to the source code, that kind of thing. And then finally, before reaching out in those communities, there's a really good guide on the Postgres wiki on how to ask slow query questions and the kinds of information that are useful for other people to help you as quickly as possible. It's also a really good guide for how to diagnose issues. So great guide there on the wiki. Those are my contact details. Email's the best way to contact me. But yeah, I'm also on most of the communities and on Twitter as well. So yeah, I think we're going to go live for questions in a moment. Thanks a lot. Cheers. Bye.